If you need to find either the atomic number or the average atomic mass, you'll need to first find the elements on the periodic table. Zinc is in the top row of the transition metal block. We will actually use zinc quite a lot this term, so it's worth remembering where this one is. Taking a closer look, we see that there are two values in zinc square. One is a whole number and the other involves some decimal places. Since we are looking for the atomic number, which is equal to the number of protons, and since protons have to be counted as whole units because they cannot be divided, the more logical choice for the atomic number is 30. Another clue that this is the better answer is that atomic numbers are generally found in the top of an element's box. Honestly, you won't use technetium very much, but it's located on the second row of the transition metals beside molybdenum, which we will use from time to time. The atomic number is again the whole number found near the top, in this case 43. Subatomic particles are inherent to an atom or an ion of a certain element. If we happen to have more than one atom of that element, then super. That just means we will have more than one of that very same collection of subatomic particles. Since the atomic number represents the number of protons in an atom, if we have more than one atom of the same element, they will all have the same atomic number, and therefore the same number of protons. Start by finding chlorine. Reviewing its entry, we see that it has an atomic number of 17. Each of our 6 atoms mentioned in the problem will also have an atomic number of 17. So we can simply multiply the atomic number of our atom by how many atoms we have. This gives us a total of 102. Note that this is just an exercise to get you used to using the periodic table, as the sum of however many atomic numbers isn't all that useful to the chemist. But the sum of however many average atomic masses actually is, and we'll use a similar argument when we get to that point. The first group of the periodic table starts with hydrogen. Unless you are asked specifically for the metal elements or told to ignore hydrogen, you'll want to include it if you are asked for things about this group. Review the entries in the column and identify the atomic number for each element. Then simply find the sum of all of these values, which is 213. Note that again, this is just an exercise. Right now we're just trying to use the table. We don't know enough chemistry to use it well. We've used the atomic number quite a bit in these problems. This example asks us to locate the average atomic mass instead. This is the number that includes the decimal places in an element's entry. If you regularly use a periodic table and there isn't a value of decimal places for the majority of your elements, you just need to find a new table. Fortunately, this version of the periodic table is the only one you get come quiz day, so you won't have that problem on that day. The average atomic mass has decimal places because it's based on the sum of the actual masses of the subatomic particles present in an atom. And as we saw in the last section, those subatomic particles have a lot of decimal places associated with them. Now, locate potassium on the periodic table, then review its entry. You'll see that it has an average atomic mass of 39.10. Eventually, we're going to get to the point where we realize that we can round these average atomic mass values, but for now, include all of the decimal places. It's worth noting that potassium is one whose element name and symbol are poorly paired. You'll use potassium a lot in this course, so it's worth making a special effort to recognize it. Manganese is another that students confuse with other elements fairly often. It's located on the top row of the transition metal block of the table, and it has an average atomic mass of 54.94. Our last one, which is actually a preview of section 1.5. Everyone loves some foreshadowing. We're asked to sum the average atomic masses for a single oxygen atom and 2 hydrogen atoms. Begin this by locating both of these entries on the table. The average atomic mass of an atom of oxygen is 16 atomic mass units, and the average atomic mass for an atom of hydrogen is 1.01 atomic mass units. To answer this question, we'll take the mass of the oxygen atom and add the mass of the first hydrogen atom to that, and then add to both of those the mass of the second hydrogen atom. This gives us an overall total of 18.02 AMU. The units were left off parts of this calculation on the slide so that you'd be able to read it more clearly, but do know that the average atomic mass always has units associated with it, even as it comes off the periodic table.